I'm the last one. You've made it. Thank you. Thank you for sticking around. Take a deep breath. One more. We're good to go. So my name is Steve Mairs. I work over at the JCMT. I'm kind of like a wolf in sheep's clothing over here and amongst all the interferometer folks. But I was asked to talk about single dish radio astronomy. That's a lot to cover in a half an hour. So I'm just going to hit some highlights, and I'm also going to link it into interferometry because, so most of you are here for. So just to give you a bit of an overview, I'm going to talk about single dish stuff, why size matters, the importance of a single dish in physical analyses as well. Interferometers are amazing and fantastic, and we love our SMA and ALMA colleagues. However, single dish is extremely important. I'll also give you sort of an overview of some science, rather than a lot of technical details and equations. I want to show you what some kind of science happens with single dish astronomy in general. But I'll be drawing examples from the JCMT because I worked there. Then I'm going to get into the short spacing problem and combining single dish data with interferometric data, and I'll show you at least one technique to do that. So once this comes through, up here we have this beautiful image of the Parkes telescope. That's down in Australia. We've got ERAM over in Spain. We've got FAST, which is really big. It's 500 meters across. And then, of course, we have the best telescope in the whole world. So I'll say single dish for this crowd, the best single dish telescope. So what we have here is the JCMT. It's covered by a membrane that helps us keep climate control and weather and everything off of our dish. That membrane that you see there is made of Gore-Tex, and that's about 97 or 98% transmissive at submillimeter wavelengths. So we like to keep a jacket on our telescope, especially these days it gets cold up there. There's some obvious examples missing from here. There's Effelsberg and the Jodrell Bank telescopes, but there's single dish telescopes all over the world, and they work together, and most of us like each other. So that's a little bit of a delay. There we go. So this was covered excellently by Dr. Williams yesterday, but this is hitting the point home that larger telescopes are better. More bigger, more better. When you have something that's 300 meters across, you can see how the resolution, which is on the y-axis or the full width half max of the beam, goes down as a function of frequency. So you can have your Arecibo on the left. FAST is even bigger now. You have something like the Green Bank telescope, something like the JCMT, and something like an SMA dish down here. Also, it's better if you have a bigger telescope for sensitivity. We touched a little bit on the fact that, a 500 meter single dish telescope is going to be much more sensitive than a 500 meter interferometer array. And the devil's in the details really here. The sensitivity depends on the effective aperture. And we like to hide things in there, like the aperture efficiency. But you can see that the diameter of the telescope is directly proportional to the sensitivity. And the aperture efficiency depends on a whole bunch of other stuff that talks about the shape of this curve. The point is, bigger dish is better. Now, I actually had this slide in here as well, but I was going to take it out, okay? But I kept it in. I kept it in because, Jonathan Williams covered this yesterday, had this up here. I just want you to realize that this is a very important tradition for radio astronomers. You can never let them live this down, GPT, okay? So when you're giving talks a few years from now, I want to see this on you. This is 32 years ago, okay? And we still haven't let it go. Nobody got injured. We find it kind of funny. Okay, so what we're going to do here is look at the same region at different scales, right? This is a horribly misleading map by Planck. So this is from the Planck Consortium. They convolve magnetic fields with flux, and it guides your eye in weird ways. But the thing is that space telescopes like Planck here, they cover wide areas of the sky, but at very poor resolution. The resolution for Planck is arc minutes, 5 arc minutes in some places. So it's very difficult to get good detail, right? So if I just take this little rectangle here and I zoom in, this is what the JCMT data looks like of Southern Orion A in the same extent, right? We have a lot more detail than you can get out of a map like that, but not as much detail as an interferometer could get. If we do the same trick and I put a little square here, I can show you some SMA data that's taken of the same region. The point here is that we need in a generation of ever-increasing complexity in multi-scale physics, multi-scale problems, what we want to do is connect the largest scales, especially in a galactic context, the largest scales available to us to the smallest scales. And we cannot do that without this really crucial intermediate scale. And that's what single dish telescopes are really, really good for, is getting larger scale structure than interferometers can and higher resolution than things like these space telescope programs can. So it's only by combining all of these data sets can you really flush out all of the good physics that's occurring in the regions that you're interested in. So I'll just talk a little bit about the science of JCMT because that's what I'm most directly involved in. But you know, we've definitely touched on it throughout this whole workshop, or at least the last couple of days. That you have different flavors of observations. With single dish, it works a lot like interferometers, but we have continuum, we've got spectral data, polarization, which was just covered beautifully, thank you, and variability and time domain stuff, which is interesting as well. Actually, this image here was taken 6 days before this one when we saw a flare bursting in Orion, which was super cool. We can track things like this in real time. I'll get more into that. So the kind of things that we're actually interested in, for one, is, you know, at the JCMT, star formation and the evolution of star-forming regions, looking at the very earliest stages of star formation, where we have, you know, some complex structures that are made of gas and dust, probably going on to form stars. We can look at the fragmentation and figure out how the mass is accreting on here. And we can also combine our data, radio, millimeter, submillimeter. We can combine that with infrared surveys of young stellar objects, or YSOs. So on this plot, for instance, the y-axis is the concentration. That's how peaky your gas or dust structure is. And on the x-axis, we have the Jeans criterion. It just means that the further right you go, the more unstable you are to collapse. So you can see that peaky things are more unstable to collapse, and the legend there shows you different types of young stellar objects associated with these. So we get to probe the earliest stages of star formation and then compare that with the youngest known stars to start getting a little bit further along in the theory of star formation in general. But there's a whole bunch of other things that you can do too. Beyond these filaments and star-forming cores in the interstellar medium, we can use Planck as a view telescope, actually. I mean, Planck, like I was showing you, has pretty poor resolution, but it shows you where a lot of gas and dust is. I've got friends over at Planck, you know, they're trying to look at things far, far away, CMB. They're like, oh, look at all this gas and dust in our way. Guess we'll throw it away. And we're like, no, my science. So we have to, you know, actually extract everything that we can from the positions of what Planck observes and then go after it with other single dish and interferometric telescopes here on the Earth. This is a really cool project going on right now with evolved stars. Using single dish telescope like JCMT, you can actually be looking at AGB stars, asymptotic giant branch stars, and how they pulse and give off material and dust to the surrounding environment. And you can track the variability over time, and you can measure the different pulses that it's had in history. That's really cool. You can also look at nearby galaxies. This is a combined image from Planck and Scuba 2 on the left there. This is of the Andromeda galaxy, so you can look at dust and gas conglomerations in our nearby galactic neighbors. And we're also really, really good, actually, if I do say so myself, at looking at distant, very distant galaxies. I mean, if you do some of the conversions from redshift, this is, 10, 11, 12 billion light years away, where we're actually looking at galactic building blocks. And we'll do number counts to try to reconstruct, the star formation history of the universe out to our cosmic horizons, which I think is super fun. As far as spectroscopy goes, there's this excellent, there's a few excellent examples here, but we can make spectra across a grid in the sky. That's in the top left there. And we can measure abundances of many different molecules, or so this is HCO plus, for instance. There's really simple molecules that exist in space that tell us a lot about the energetics, the kinematics, It shows us what space is actually made of, which is really interesting to a lot of people. And over to the right here, it's an example of how we identify tracers. On the y-axis is the luminosity in infrared, and on the x-axis is the luminosity of HCN, the 4:3 transition. So if you have no infrared data available to you, it looks like you can measure the HCN and you can derive the infrared data and then do some physics because it's a well-correlated relationship. Down here, we're doing some kinematics, figuring out thermal line widths, whether there's turbulence. There's an adage I really love that I just heard at the AAS last week, so I'm going to pass it on to you too if you weren't there. A picture may be worth 1,000 words, but a spectrum is worth 1,000 pictures. I think that's really cool, and that summarizes a lot of what you can do with spectra. Polarization was just covered, so I don't have to go into this a lot, but this is an image that my friend Kate Paddle made showing the polarization vectors up the pillars of creation. And so we can combine different wavelengths from here and actually see what's going on with material flow and large-scale magnetic fields. Also, there is variability, and single-dish telescopes really shine here. And I want to point out, for instance, the JCMT, surprise. We're doing a consistent monitoring campaign of embedded protostars in their natal envelopes. So we're actually looking at the dust heat up and change as protostars go into accretion bursts. And we're doing this in real time. Some of these vary on scale of hours, some vary on the scale of weeks to months, and we can actually watch that. The trick is that you want to get as many objects as possible in your field of view. So statistically, you're going to see something. There might be a flare or something. Each circle that you see here is one JCMT observation. It's 30 arc minutes in diameter. So when we look at all of these 8 observations, it takes us only 4 hours to get that data, and we have information on over 2,000 sources, and we can construct light curves like the periodic one that you see here or in the GIF here. This is a protostar going into an outburst. Without the wide field of view and being able to track these at a consistent monthly monitoring campaign, it's very difficult to do science like this. Talk about why proposals are rejected. If I asked for all the SMA time, I probably wouldn't get it, but you know. And one interesting thing is that you can combine all of these different flavors together, right? And somebody asked about the magnetic field strengths as well. There's one interesting thing that you can do. It's called the Davis-Chandrasekhar-Fermi method. Just rolls off the tongue. When you want to find magnetic field strength, B over here is the magnetic field, of course. POS stands for plane of sky. It's not what you mumble when you're calculating magnetic fields. But yeah, this is the plane of sky. And over here, this column density comes from continuum observations. This is a velocity dispersion from spectral observations. This here is the dispersion in polarization vector, which comes from polarization observations. And when you put it all together, you take 2 or 3 observations and you can see whether these things vary over time as well. So if you're looking for interesting, ideas for proposals, or you're looking at what you can actually do with a few different well-calibrated instruments, you can certainly come back to these slides and check out some of the things that we do regularly at Single Dish. I also want to highlight a couple of things. Single Dish, we can use detectors sometimes that interferometers can't. So, bolometers here, if you've never heard of a bolometer, you can think of it like a super-cooled thermometer. It's also super cool, but it's super cooled as well, like by the actual definition. Here, when you're really close to the transition edge, so the transition between super cool and just regular cool, when you have a little change in temperature, that relates to a big change in resistance in your circuit. So light can actually warm up the thermometers, the resistance changes, and if you remember, high school physics, when the resistance changes, the current changes, that generates a magnetic field, and we can measure that and make images from it. Bolometers are actually super fun. I think that we have still consistently the coldest place on Earth at the JCMT. Who knew it was in Hawaii, the coldest place on Earth? But it's we keep our instrument at about 0.075 Kelvin all the time. because that's where this works, is down in that regime. We have to fight the atmosphere, of course, just like interferometers. I'll give you a brief example here. You know, the signal that is measured by a single bolometer is a function of time, and that depends on a scaling factor. There'll be some gain between all of the different bolometers that you're using. Our main instrument has about 10,000 bolometers inside it, and all of them have slightly different gains and things like this. The atmospheric extinction is, of course, important. How much water vapor you have in the sky, what angle you're looking from zenith. You actually want to study the astronomical signal and extract this, but there's a whole bunch of noise that tries to stop you from doing that. Some of the main sources of noise are just uncorrelated white noise, things that you cannot improve on unless you just observe for longer. There's also the common mode noise. So, I mean, imagine a big cloud moves in front of the JCMT. All of the bolometers are going to react to that in the same way, but it's not out in space. It's an Earth thing that we want to remove. So we have to model that and take it out. And then there's also this excess low frequency, sometimes known as 1/F noise, that we have to care about too. So a lot of the data reduction that we do, especially in Continuum here, is modeling these different types of noise, correcting for the atmosphere, and then extracting our astronomical data that we're actually interested in. I'll also note very briefly that MKIDS are like the cool kids in town now. Everybody is moving towards MKIDS or has moved towards there. These are amazing. I find this amazing. You have light here that hits a superconductor. It breaks a Cooper pair, it makes a quasi-particle. The details aren't, specifically important. But what you have is light hitting this attached to a capacitor, and each of these little receivers will resonate a little bit. They'll resonate at a specific tone that has something to do with the amount of photons that are coming in. So each one of these things resonates in its own little tone. So you make an array like this, and when you put them all together, the tones come together in this kind of beautiful symphony. And what you're able to do is go from the resonant frequency of each one of these little detectors back to an image on the sky. And so the JCMT is going to be installing a beautiful array of these by 2023 to match Toltec and Blastpole, if you've ever heard of those. So Simon Radford talked about a little bit about how in Single Dish we use differential techniques to get rid of the atmosphere. And this is kind of fun. If you take your 4 arrays of bolometers, like at the JCMT, what we do is we scan across the sky continuously. This is actually called a Pong map. It's just like the video game Pong. You hit an edge, you turn around. That's all it is. And you keep on scanning across the sky, so you go over the same parts of the image from multiple position angles over and over again. And then we know that the flux that's, broad and it changes all the time, that's the atmosphere. And the flux that stays the same and is stable, that's your astronomical signal. So it's one of the ways that we use a differential map to extract the astronomical signal from the atmosphere. It's not perfect. We still lose some large-scale structures. However, it's a different process and not in the same scales that interferometers lose large-scale structures. So this is an interferometry school, right? So interferometry's short spacing problem is, as advertised, a problem. You want those large scales, right, in your image. And I'll show you why in a couple of different ways. But I used to observe with the Jansky VLA, but that was before it was the Jansky VLA. You can't squish dishes together to fill in all the gaps. They get really mad at you when you try to do that. It sometimes costs a lot of money when you whack telescopes together. The problem is that you'll always have this hole, as many people have pointed out. Your largest angular scales are lost in an interferometer, and you can't get them back. The effect that this can have on data, and this has already been touched on, is, if you have your ideal coverage here, you get sort of the sync function out the other side. But if you subtract all of the short baselines and you take the Fourier transform, it turns out that you get these things called negative bowls, right? So an example of this that I have shamelessly stolen is that when you look at a bright source and you have negative boles next to it, you know that there's probably some more large-scale structure there that might actually be important for the science goals that you're going after. If you're missing flux, you can't calculate a good mass, you can't do a variety of other things. So you have to know very much the limitations of the data when you are missing that background large-scale structure. So there's a couple of ways to get these short spacings. So if this is, the spatial frequency, the spatial frequencies that you're sensitive to, this is about as close as you can get your telescopes together, and then you can widen an interferometer out to Event Horizon Telescope, the moon, wherever you want to go. But this inner part is missing, right? So you can do a couple of things. You can extrapolate the short spacings by some model. You can do this using clean, and you can try to, figure out the larger scale structure and mathematically solve for it. Or you can just go measure it, which is kind of cool. A single dish, now get this, is kind of like an interferometer, except it's a lot easier to set up. All it is, right, really, if you break a single dish apart into all of these different infinitesimal pieces, you just have baselines that run from 0 to the diameter of the dish. We just don't have to do anything fancy and complicated to put it all together at the end. It just all focuses at the same time together. So thinking about a single dish like an interferometer, you go from 0 down to the diameter of that single dish, and you combine these two things together to fill in that UV plane. And then that's a real measurement, and it's pretty robust, actually. Sounds simple, right? Which dish should you use? Well, you want to maximize your UV range. So the best thing to do is to use a single dish that's larger than the minimum separation of your interferometer antennas. So here's a couple of examples. So I work at JCMT, so this might be biased, right? But I have heard that part of the SMA design was specifically to be designed to work with JCMT in this way. Is that true, SMA people in this room? Anybody knows? I'm going to carry on that way if that's it. Yeah. All right, vindication by silence. So what we have here is one example where we have the SMA only, and then somebody filled in these central 0 spacings here with the JCMT. Look at the difference in these maps. This is CO2 to 1, right? I mean, you don't see these fingers out here. You're missing a lot of large-scale structure in and around here. That's going to throw off mass estimates. You don't get the full kinematics or anything. And that's all from filling in this central region of the UV plane because these people have done it actually very well. But, this isn't the only combination you can have. You can have the JVLA with the Green Bank telescope when the JVLA is in its more compact configuration. Green Bank telescope's about 100 meters. Arecibo is about 300 meters. So when JVLA goes out to more extended regions, you can combine it with the larger single dish telescope. Atka and Parks is a really good demonstration. Historically, CARMA-NRO. I really miss CARMA. I observed out there. That was a great telescope. Like Jeff said, rest in peace. That's a beautiful thing. But there's still archival data available too. So just a very quick primer on combining single dish and interferometric data. The first thing to go do is to go read this. It's from 2002. A while ago, but it is amazing. It will give you all the background that you need. A lot of theory is right there. It's really fantastic. First, you got to compare apples to apples, right? You got to find a scaling factor that calibrates the flux between the interferometer and the single dish telescope. So just the canonical typical equations that I'm going to throw up here are the how you calculate the flux. But pretty much the flux calibration factor is really simple. You look at the flux measured at the interferometer, and you compare it to the flux measured at the single dish telescope. And you make sure that they're the same, because that should make sense, right? There's a caveat here, though. You have to use the overlapping UV coverage. You have to compare apples to apples. So if this is your UV coverage, your interferometer data can extend out however far you have, stations to put your telescopes. And the single dish data covers this inside part. In the overlapping region where both the single dish and the interferometer are sensitive, that's where you want to do your calibration, because you're looking at the same flux, the same scales of flux, and that's where you want to calibrate. Here's another slide I shamelessly stole. What you want to do is this combination in the UV plane. You can try in the imaging plane, it's not good. In a pinch you can do it, but the best way to do this is to combine them in the UV plane. This is called feathering. If you hear people say feather, it's because you're layering the single dish data in with the interferometric data, so it's like feathers. I'm not a biologist, I don't know. But what you have here is a single dish. You take the Fourier transform, interferometer, take the Fourier transform. Compare the flux in the region that you're both sensitive to, multiply by that scaling factor, add them up, and go back to your image plane. And now you have high resolution with the large scale structure intact, which is really fantastic. That's just one example. This is an example from ALMA. I'm sorry, I know it's the SMA, but like they have a really good example. So you take a M100 here. It's an interferometer. On CASA guides here, you can go in and you can run this in Python yourself. This website shows you exactly where to grab this data and how to combine it yourself. It's really great. It'll show you how to regrid the data, how to multiply the single dish by the interferometer's primary beam, because you want to get non-uniform. You want to have the same non-uniformity between the two beams, I'll say. It shows you how to combine in UV plane. This is a command in CASA or Myriad or APES. Don't use APES though. But it's a command in CASA, or I'm sorry if there's anybody who does. But you just say feather, and you give it just its switches and parameters, and it will feather your data for you. And like always, you change your scaling factors and your weighting, you turn up the Briggs, whatever you like to do, and it shows you here how much large-scale structure you're missing, which again affects all of the physics here. And in the final minute, one more example that I was involved in. This is from the CARMA-NRO Orion survey. So we used the CARMA interferometer and the Nobayama 45-meter dish. It's described in this paper down here in detail because we kept on reading all of these papers and say, but how did they combine this properly? So we just wrote a huge section on exactly step-by-step what to do. This is the CARMA image of Orion. This is the NRO 45. Can you tell a difference? And when you combine them together, you get, when the pixels show up, a wonderful substructures at 7 arc-second resolution down here with all of this beautiful structure out here too. And you can do this over very wide fields spanning several degrees. This is the whole Orion A complex from north to south, including the famous Orion molecular cloud there. So this is the kind of stuff you can do when you feather in your single dish data into the UV plane. So I'm just going to leave a summary up there, and I'll take any questions. I think that's it.
So I've been keeping up vaguely with the news about Nama-Kanui, but like, what does it actually do compared to, for example, Scuba 2 or the other instruments that are already active at JCMT?
At JCMT, so Nama-Kanui, for those who don't know, is our new instrument that we just got at the JCMT. So that one's not based on bolometers or anything. Those are like the SIS sort of detectors that you've heard about. It has 3 cartridges in it, 230 gigahertz, 345 gigahertz, and 88, I believe. The 230 gigahertz is being commissioned first, so we can continue on with our VLBI and our Event Horizon telescope and everything like that. But we're matching ALMA's instrumentation, which is one thing. It's much, much more sensitive than our last instrument, which was Receiver A. Receiver A was the one, because it's in the A band, Receiver A was the one that helped measure the black hole with the Event Horizon telescope. It's done an amazing variety of things, but it was also older than some postdoc fellows that we have working at the JCMT. But yeah, so the new instrument is much, much more sensitive. It'll have 3 different cartridges on it, and it'll be one-to-one consistency with ALMA and the Greenland telescope as well. Yeah, great question though.
So with this factor that you talk to put the flux densities at the same level, so if you calibrate the data and flux density separately, why can't you just assume that you did a good job in the interferometric data and the single dish and just add calibrated data?
I mean, it's one of those things about how much you like. Yeah, probably your data shouldn't be too far off, right? It probably shouldn't be a factor of 4 difference or something like that. But when you're combining data from Nobayama in Japan and CARMA, which was on the border of California and Nevada, there's a whole bunch of different atmospheric considerations, instrumental considerations, and there's systematics that you want to correct for outside of the other flux calibrations as well. So this is making sure that your data comes into alignment. But it's not your overall flux calibration factor. The other ones should already be flux calibrated before you do this. Yeah.
So for the Orion image, when you were those created with feather in CASA or?
So yeah, they were combined in the UV plane.
I thought those are done in Myriad.
I think that was done in Myriad actually.
Okay, because this is the comment about feathering. I think when you supply the single dish image, the image itself is not being deconvolved with the primary being of single dish. So that is not it's an imperfect way of combining single dish with Fragmentation.
Right. Yeah. There's some preparation that you have to do, exactly like deconvolving with the primary beam, and so the ALMA tutorial that I put up will show you all of the initial steps to do before the feathering takes place, like regridding and deconvolving, and making sure that you're consistent with one another.
That's right. I think the issue, I think the people taking just the single dish image with interferometer, and that will be a problem when you combine it.
That's right. Yeah. Yeah, that's a really good point. All right.
If there's no more questions,